undergrads have been working on a project together and made some not only great research, but some very noteworthy research that you may have read in many of the trades this last week. It's been kind of fun from this side of keeping our lips closed because we knew it was coming and they needed some time. But instead of me talking about it, I'll let them introduce themselves and talk about their research. But this is like a proud father moment for me. I love when our students do unbelievable great work. So way to go, boys.
Thanks for that introduction, Father Joel. My name is Robert Morton. I'm a PhD student here. This is Dan Sokoler and Austin Klasa. We did a research study under the Ensure project, which is kind of a unique project directed by Dr. Melissa Dark and Dr. John Springer. And we tried to look at an observational study in this particular research project that dealt with Cisco VPN streams. That was kind of the project that we were tasked to look at. This was an interesting study because it had a lot of ups and downs and kind of different paths. And we found some vulnerabilities that was very surprising to us. So we want to explain a little bit about what we found, how that relates to some of the work we're doing in the future to try to quantify that. So it kind of started out as an observational study to really look at if there's any information leakage from Cisco virtual private networks. As all of you probably know, Cisco virtual private networks are used to connect businesses and organizations worldwide. And so we were trying to look at this particular VPN device to see if there was anything we could learn about it. Could we learn about the private communications that were occurring within the virtual private network? Some of the questions we were trying to answer initially were just some simple W's. You know, what communication occurred? When did the communication take place? Where did the communication take place? Could we actually understand who was communicating and why they were communicating? And we wanted to see where we could answer those questions and if encryption actually helped or the Cisco virtual private network actually leaked information. One of the salient things we saw that was surprising to us is that we believe that Cisco, after it was initiating some of the secure encryption for this Cisco VPN device, is that it was using a new protocol called QUIC, which is developed by Google. QUIC is a protocol that was designed to have equivalent security to TLS and SSL. It was to have encryption, but it was also to reduce latency and essentially make the internet fast again. It does this by reducing connection and transport latency because it uses UDP. And so this was one of the things that was surprising to us that we believed we didn't understand why they were necessarily using QUIC, and so we had to investigate what QUIC was. What we learned is QUIC and the internet has been transformed over the last 5 years with these kind of new protocols to make things faster. Everybody wants a faster encryption algorithm so that you can, watch Netflix or do video streaming or just make things faster. So we started to learn that QUIC is used in Chrome by over 1 billion users. There's hundreds of thousands of websites, and by default, Google proper, such as Google.com, the search engine, YouTube, all use QUIC as their main protocol. So I wanted to talk and turn it over a little bit to Dan, who's going to tell you about some of our initial findings of trying to answer those W questions. Who's communicating, why are they communicating, what information leaked from the QUIC protocol.
So knowing that this VPN uses QUIC, we decided to run some different types of traffic through it to see what it did, what information we could get out of it. And so we started with web and FTP traffic. And what we found was that within each different type of traffic, it was very consistent. The packet size was consistent, the sequence of packets was consistent, but across the different types of traffic, there were differences, most notably the packet size. So for web traffic, we found that QUIC was consistently breaking it into sizes of 1392. And for FTP traffic, Quick was consistently breaking it into sizes of 1463. And that allowed us to actually determine what the user was doing. Were they browsing the web? Were they transferring a file? So this is us beginning to determine what the user's doing, their habits, stuff like that. In addition to web and FTP, we ran some IRC traffic through it. So initially we started with just some basic connecting and disconnecting. And what we found was that each connect and disconnect had a pretty specific signature. Sequence of packets, as you can see up here. Typically 2 TLS packets followed by a very specific set of quick packets. And because we also have access to the source and destination IP, we can keep track of individual users connecting and disconnecting to IRC chats within the VPN. And this is obviously a pretty significant leakage. So beyond just connecting and disconnecting, we took a look at specific chat communication within the VPN. And what we found was that nearly all of the messages were beneath 300 bytes. And for most of them, they were all different sizes, which was a little concerning and a little confusing. So when we ran it a bunch more, we started to see some more consistency within that. I'll turn it over to Austin to explain a little bit more about that.
So as we started to test IRC chat communication further, we decided to send messages with an increasing size, just sending one character more each time we sent a message. And we see this really nice stepping function when we listen to the unencrypted side of our network. However, when we correlate these packets with the encrypted side after it goes through Quick, we see this same really nice stepping pattern with 16 bytes of padding that's used by Cisco's implementation of Quick. And from this, we can start to piece together some more information. So when we think about AES-GCM, the key space should be 2 to the 128 bits. And that works as expected. But when we start to look at AES-GCM in Quick, we see that the message space is much smaller than that, since we now know what the length of the individual messages are. So in our study, we were able to successfully fingerprint web, FTP, and IRC services, look at the number of IRC clients that are connecting and disconnecting in an encrypted Cisco VPN, and we were able to identify individual IRC chat message links. So in conclusion, this unintended consequence of containing packet size loss is that these ordinal patterns start to emerge. And when we start to view these patterns and look at the larger picture, we're able to see that these specific pieces of information start to occur. So with these identification of the IRC message links, it suggests that Quick is more susceptible to traffic analysis with sensitive and short and spontaneous types of communication. So one of our next steps Rob will explain this real quick.
So I think you're probably wondering, okay, there's some information leakage, what's the big deal? We're learning that there's some web traffic, some FTP traffic, this is not necessarily new. So I want to explain a little bit about a proof of concept exploit we're going to show you of how to bypass authentication in Gmail using the leakage that Quick tells you about particular password lengths. And I want to talk a little bit about the limitations as well as the adversarial model that we kind of put together as this proof of concept. So the limitation is that Quick actually leaks and tells you the exact length of the password of someone typing in their username and password. So you can start to do a process of elimination of, is it 8 characters? Is it 7 characters? And we're trying to quantify right now with Dr. Blocky and Ben Harsha on what is that actual damage? What is the advantage that you have as an adversary just from leaking the password length? So we came up with an adversarial model. This isn't necessarily going to help you get the most complex password. If you have a very complex password that's 30 characters long, this isn't going to give you much of an adversarial advantage. But we know that the adversary has a lot of information today. There are lots of data breaches occurring. So for instance, the Yahoo data breach, there was 1.7 billion passwords that have been leaked about what people are really using for passwords. So think about the adversary now knows this. Also picture that the adversary is looking to conduct a campaign. The campaign is looking to go after political dissidents or a particular minority religious group. And I want to get into the Gmail accounts of that particular targeted group. This is the adversarial model that we put together. Also, think about the system of Gmail. Let me go over a couple things that Gmail does. Gmail does not lock you out if you put in multiple passwords. It uses a system called CAPTCHA to simply increase usability so it actually tries to see if you're a real human being to kind of delay an online brute force attack. But it never locks you out. It also never emails you if there are multiple online attacks being done in Gmail. So the user never knows if someone's trying to guess 1,000 passwords or 2 passwords or 5 passwords. Also, Gmail does not require complex passwords. The only requirement is between 8 characters and 60 characters. So now when you combine that with leaking what the real length is of a particular password from the QUIC protocol, if you're sniffing a target network, again, our group that we're targeting is perhaps a political dissident group or a minority religious group that we want to get into those accounts. Can we gain a foothold into some of those accounts? And if we do, could that help our campaign to go after the rest of the users? For instance, if I get into a couple accounts, could I then start spearphishing the other accounts? So the idea isn't about total system compromise, but does it give the adversary enough an advantage to target a group? Our initial results is that we believe we can get in with some password lengths. We can get in using empirical evidence from past password breaches, such as the Yahoo data breach, potentially getting into accounts with a 10% chance. That's quite an advantage for an adversary. And so we're going to show you how we apply this to a real online attack against Gmail as a proof of concept. Austin's going to explain a little bit about the proof of concept exploit he wrote and the steps required to make this a reality against Gmail to bypass CAPTCHA, to use a commonly used password that we've gotten out of dictionaries, such as the Yahoo data breach, and actually perform an online attack that would not be, that the user would not necessarily know is occurring. So I'll let Austin take it over and kind of walk you through his proof of concept exploit.
So before I begin, I'll talk about the 3 steps that this proof of concept is showing. So the first thing that you'll see is a bot simulating a user signing on to Gmail multiple times. So it'll do it 3 times while we look at Wireshark in the background, and we'll capture that traffic. In step 2, we extract the password length, and we create an optimized password dictionary that only contains passwords of that specific length that we detect. And step 3, we try to brute force the system. So right now it's signing on multiple times, like I said. And this just shows what an average user would do when they're signing on multiple times, and shows that if we have access to the network and we collect these packets over a length of time, we can start to gain this information. So as this is happening right now, we're running Wireshark in the background, collecting all these packets that are being sent across. And it's right now working on step 2 and detected the length, extracted the password length from those packets. And we're signing on to an anti-captcha service extension that we can use in Chrome to automatically solve the captchas for us. And as it's working right now, it's going to try the passwords in this optimized dictionary. So since we know the length, we have a pretty big advantage, and we can reduce the number of guesses that we need and reduce the cost of getting into the system. And then, as Rob said, we didn't find any sort of rate limiting or anything like that, or any account lockout on the Gmail system after we log in. And the best way to get around this is using two-factor authentication. So most of the delay that you see in the program is actually delays that we built in ourselves. This could be a little bit quicker, but for demo purposes, we want to make sure that everyone can see what's going on and we can see that it's working correctly. So multiple different types of services could have been used in this case. We just happened to use the Romola service, but others would have worked as well. And this attack is scalable, so we can run this with multiple different bots at the same time to try to get into one account. So after it enters the correct password, we can see that we can get access to the Google accounts that we're trying to target. And that includes all their account settings, Gmail, calendar, and all of their Google services that they might use.
So I did want to talk about disclosure. We did inform US CERT. We also informed Google, Apple, Microsoft, and they're looking at particularly ways to look at some of the underlying encryption algorithms that are used in Quick. Also, where those encryption algorithms might leak information and how to deal with it. So they're meeting with the Web Consortium. We have some more information at ringroadbug.com. And we'll be updating a little bit about how we actually quantify that over the next couple months, about what is the actual advantage you have in situations like this when protocols actually leak information. We'd like to thank several people that really helped with this. We'd like to thank Dr. Dark and Dr. Springer for being our leads in this particular project. We'd also like to thank Bill Layton and Mark Lupker for all their great support on this and advising us as we went through the ups and downs of this particular program. We'd also like to thank Stephen Frank at WinTech, who kind of helped us with setting up the Cisco lab, and also Adam Hammer, who helped us set up the Cisco lab. And thanks for Dr. Spafford and Dr. Blocky for making sure that we properly articulated our limitations and our capabilities with this particular exploit. So that's really the end of the presentation. We're happy to take questions, but I know we're also bumping up against lunch, so I'm sure everyone's also very hungry. The disclosure? Yeah, so We've gotten some mixed reaction. It's difficult because it deals with a protocol that is used in Chrome, and so there is some discussions at Google in particular about, is this a protocol vulnerability or like a product vulnerability? And of course, that's very important from fixing the problem about which business unit you're using. So they're in discussions about that. Apple initially is looking at trying not to use some of the underlining cipher suites to transmit sensitive data, particularly AES GCM. They're looking at alternatives. I don't think they've come up with what they're going to be using, but I think they're looking at some previous ones like AES CBC HMAC. That's just a potential. I don't think they've made a decision on that. But I also think one thing we've really learned about this is how difficult it is to fix these types of things, to make sure users can still be able to use web browsers, those types of things. So I know that they're bringing this to the Web Consortium to try to see if they can fix it at the HTTP layer in the standards body with HTTP2, where they can actually identify when am I sending sensitive credentials like passwords, and can then I pad and obfuscate their length. That's one potential solution. So there's a number of different areas and discussions that are going on. But because Quick is so pervasive, I don't think it's going to be an easy fix. So we've tried to show a proof of concept exploit, but not necessarily develop something that would be used in the wild. I think we're still going through the initial results. I think yeah, sorry about that. Thank you, Joel. The question was, most people probably use 8 characters, 9 characters, 10 characters for their password. So knowing that, how much of an advantage does that really give you when you leak the length? I think we've quantified initially that it doubles your advantage. And the reason for that is that I now can create an optimized dictionary and do an online attack, where previously I might have to do the passwords of all of those. And so an online attack may not be possible in that particular case. That's different for an offline attack. And that's something we're still quantifying, but I think our initial results are it doubles. So your advantage doubles.
Any additional questions? Gentlemen, thank you very much.